students, welcome to Sunil's tutorial. I'm Sunil Midwani and today we'll be doing this chapter called as current electricity. Let's see this. Let's see some basics first. What do we understand by an electrical network? What do we understand by an electrical network? An electrical network is a combination of various circuit elements and electrical sources connected in a complicated manner. Simple language, everything that is connected in the circuit forms an electrical network. So what is an electrical network? It is a combination of various circuit elements and electrical sources connected in a complicated manner. That's my electrical network. Next, what do we understand by a node or junction? What is a node or a junction? A node or a junction is a point in the electrical network where two or more conductors meet. It is a point in the electrical network where two or more conductors meet. Next, what do we mean by a loop or mesh? What is a loop? It's a closed path for the current. It is a closed path for current. A closed path for current is called as a loop or a mesh. Fine. Now, once we know what these terms are, now let's first see Kirchhoff's first law. Kirchhoff's first law. Right? Now, Kirchhoff's first law is also called as the current law. Kirchhoff's first law states that the algebraic sum of the currents at any junction is equal to 0. The algebraic sum of currents at any junction is 0. That means sigma I is equal to 0. Right? So do we understand Kirchhoff's first law? Now, while determining the sum of the current or while using Kirchhoff's first law, the following convention has to be used. Convention the current approaching towards a junction is treated as positive, while the current leaving a junction is treated as negative. Current approaching a junction is treated as positive and current leaving a junction is treated as negative. Right? That's the convention that is to be used. Let's try to illustrate this with the help of a diagram. Suppose if I have a node P, I explained to you what is a node. It is a point where two or more conductors meet. Let's assume I have multiple conductors meeting at this point. Right? Where you have multiple currents coming in and going out. Let's assume this is current I1, I2, I3, I4 and I5. Now they are saying that the current approaching the junction is to be treated as positive. In this particular direction, I1 to I4 is approaching the junction, right? So that means I1 to I4 will be treated as positive. So I1, I2, I3 and I4. I5 is leaving the junction, therefore I5 will be treated as negative and the sum of the currents will be 0. Fine, do we get this in here? So this is Kirchhoff's first law. Next, let's see Kirchhoff's second law. Like how Kirchhoff's first law is called as the current law, Kirchhoff's second law is called as the voltage law. Kirchhoff's second law states that the algebraic sum of the EMF taken along any closed loop is equal to the algebraic sum of the product of the current and the resistance in each part of the loop. The algebraic sum of EMF taken along any closed loop is equal to the algebraic sum of the product algebraic sum of the products and algebraic sum of the products of the current and resistance of each part of the loop. Each part of the loop. That is sigma IR is equal to 0. Oh no, sorry. Sigma E is equal to sigma IR. The sum of the EMF is equal to sum of the products of current and resistance. Now let us see the sign convention to be used while using Kirchhoff's second law. Right? Starting from any point in the circuit, one arrives at the same point after traveling along all cells and resistance in the circuit. So while using Kirchhoff's second law, you start from the point, move through the entire circuit and come back to the same point. That's the first thing that you need to remember. Right? Now, first let's see the sign convention, then I'll show you how to use the loop. For Kirchhoff's second law of closed loop, the conventions are current which are in the same direction in the loop, same direction in which the loop is traced, are treated as positive. Current which are in the same direction, current which are in the same direction in which the loop is traced, are treated as positive. Right? While those in the opposite direction are negative. While those in opposite direction are negative. Right? So if the loop and the current are in the same direction, then it's positive. If loop and current are in opposite direction, then it is treated as negative. Next, EMF of the cell is treated as positive if the cell tends to send current in the direction of the loop. EMF of the cell is treated as positive if the cell tends to send current in the direction in which the loop is traced. I'll just show you this with an example in which the loop is traced, right? Otherwise the EMF is treated as negative. Otherwise the EMF is treated as negative. Okay, let's try to understand Kirchhoff's first law and second law with the help of an example, right? Let's consider a electrical network with EMF and resistance in it. Different sources of EMF and different sources of resistance. Right? Let's consider that this is point A, B, C, D, E, F, E1, R1, R2, R3, R4, R5, E2. Right? Let's assume that I1, I2. Right? Now let's try to apply Kirchhoff's first law and second law to this network. Right? Now, this particular network is made up of multiple loops. You can have a loop, guys. Let's see which are the various loops I can have. I can have, now remember, in a loop you have to start from a point and reach the same point again. So I can have a loop A, B, C, D, E, F, A. I can have a loop A, B, E, F, A. I can have a loop B, C, D, E, B. So there are 3 different loops which are possible here. Now I'll take one loop at a time and then let's see, consider loop. Let's consider the loop A, B, C, D, E, F, A. Right? Now, I am moving from, guys, now understand carefully because you need this in numericals also. I am moving from A to B. That means the loop is being traced from A to B. Right? The loop is being traced from A to B and the cell E1 is also sending current from A to B only. It is sending current in the direction from A to B. So as per sign convention, EMF of the cell is treated as positive if the cell sends current in the same direction in which the loop is being traced. Loop is being traced from A to B. The cell is sending current in the direction from A to B. So therefore I can say that E1. Now, current entering a node is treated as positive, current leaving the node is going to be treated as negative, right? That means current I1 is going to be entering node A, so therefore it is going to be treated as positive, so this will be I1 R1, right? So I have moved from here. Now I am going to be moving from B to C. I am moving from B to C and the current is moving in reverse direction. A simpler method of remembering it is if the current and the loop are being traced in the same direction, then current is positive. If current and loop are being traced in opposite direction, then current is negative. I am moving from B to C, whereas the current is leaving the node B. If it was entering the node, it would have been treated as positive. Here it is leaving the node, so this is going to be minus I2 R4. Fine, do we get this thing clear? I am tracing the loop from C to D, whereas EMF is sending a current in reverse direction. It is sending current, the cell E2 is sending current in the direction from D to C, whereas the loop is being traced from C to D. Therefore, the EMF will be treated as negative, right? current, this at this point you will have I1 plus I2. This will be I2 and this will be I1. Fine, do you get this thing here? Now I am moving from D to E. Is the current entering the node or leaving the node? It is going to be leaving this node at point D. It is going to be leaving the node at point D. Since it is going to be leaving the node at point D, the current will be treated as negative I2R5, right? Then I am moving from E to F. When I am moving from E to F, is the current entering the node or leaving the node? The current is entering the node, therefore it will be treated as positive. So this will be I1R3 is equal to 0. That's how you apply Kirchhoff's second law. Kirchhoff's second law says that the sum of the EMF and the product of current and resistance in a closed loop should be 0.
So can you explain why alpha is negative?
I'm going to be tracing the loop from D to E. In which direction is the current moving? In reverse direction. As I move from D upwards, is the current entering that node or leaving that node? The current will be leaving the node. Let's explain this to you with another loop, guys. Let's consider loop, say A, B, E, F, A. Right? I'm going to be tracing the loop A, B, E, F, A. Right? Now if I'm tracing this loop, then I can say, guys, let's start from A. Is the current entering the node or leaving the node at A? The current is entering the node at A. Therefore, this will be positive I1R1. Right? Do we get this thing clear? Now, from here I'm going to be moving from B to E. If I'm moving from B to E, the current is entering the node at B. The current is entering the node at B. That means the current is going to be treated as positive. The current here is I1 plus I2. Resistance is R2. Right? I'm moving from E to F. As I'm moving from E to F, the current is entering the node at E. Since the current is entering the node at E, it will be treated as positive. So this is going to be plus I1R3. Now, I'm going to move from F to A. The loop is being traced from F to A, and the battery is also sending current in the same direction. If the current sent by the EMF is in the same direction in which the loop is being traced, then the EMF is treated as positive. So this will be plus E1 is equal to 0. Fine, do we get this thing clear? Now, let's consider another loop, guys. Let us consider a loop, say B, C, D, E, B. Let us consider the loop B, C, D, E, B. I'm moving from B to C. Current is leaving the node at B. That means current will be treated as negative. So this will be minus I2R4. Right? I'm moving from C to D. The loop is being traced from C to D, whereas EMF is sending the current in opposite direction. Therefore, it will be treated as negative minus E2. I'm moving from D to E. The current is leaving the node at point D. Therefore, current will be treated as negative I2R5. I'm moving from E to B. Current is leaving the node at point E. Therefore, current will be treated as negative I1 plus I2. R2 is 0. Right? So, do we understand how to work with a loop? Now, I'll do some numericals with this loop so that your concept of loop is absolutely clear. Take down the numerical, please. A battery of EMF 4 volts. A battery of EMF 4 volts and internal resistance 1 ohm. A battery of EMF 4 volts and internal resistance 1 ohm is connected in parallel with another battery of EMF 1 volt and internal resistance 1 ohm. The combination is used to send current. The combination is used to send current. The combination is used to send current through an external resistance of 2 ohms. Find the current in the external resistance. Now, let's see this. With the sum, we can easily draw this diagram. Once this is done, let's apply Kirchhoff's second law. If I apply Kirchhoff's second law, let's take the loop AFCBA. In loop AFCBA, starting from the point, you have to always end at the point, right? Now, AF, current is entering the node at A, but there's nothing there, right? Now, AFCBA. Now, I'm moving from F to C. As I move from F to C, the EMF E2 is sending in current in the direction from C to F, whereas the loop is being traced from F to C. So in that case, this EMF will be treated as negative, right? Now, as I move from F to C, current is leaving the node at F, right? Therefore, this particular current will be treated as negative. So minus I2 R2, right? C, B. Now I'm moving from B to A. As I move from B to A, right? AFCBA. The loop is now being traced from B to A. As I move from B to A, current is entering the node. See, here you had current I1 plus I2. This is I2, this is I1. Current is entering the node at point B, right? Since it is entering the node at point B, I can term it as positive. So this will be I1 R1. I'm moving from B to C. The loop is being traced from B to A. The loop is being traced from B to A, and EMF is also sending current in the direction from B to A. Therefore, it will be treated as positive. Is 0. Now you all can substitute and get the answer. I won't do the substitution. I'll just show you how to read the loop. Right? The values are given. All you guys have to do is substitute and get the answer. Next, now consider in loop. Let's consider loop, say FEDCF. FEDCF. As I move from E to D, current is entering the node at point E, right? Therefore, current will be treated as positive. The current is I1 plus I2 R, right? As I move from D to C, there is nothing there. Then I'm moving from C to F. As I move from C to F, current is entering the node at point C. Since current is entering the node at point C, therefore the current has to be treated as positive. Current is entering the node at point C, therefore it has to be treated as positive. I2 R2. I'm tracing the loop from C to F. I'm tracing the loop from C to F. EMF is also sending current from C to F. It is sending in the direction. Yeah, the EMF is sending current in the direction in which the loop is being traced. Therefore, it will be treated as positive. Is 0. So I'll get one equation from here. I'll get another equation from here. Solve the two equations simultaneously. You should get your current. Right? Next, let's see another sum like this. I have not completed this. You will get two simultaneous equations. You will get two linear equations. Solve the two linear equations simultaneously. You will get your answer. Next, take the next one, please. Two cells of EMF two cells of EMF 2 volts, EMF 2 volts and 1.5 volt and 1.5 volt with internal resistance of 1 ohm each, are connected in parallel with similar poles joined. With similar poles joined. The combination is connected to an external resistance of 10 ohms. The combination is connected to an external resistance of 10 ohms. Find the current in the external resistance. Find the current in the external resistance. Find the current in the external resistance. Right? Let's label the loop A, B, C, D, E, F. Okay. Now this is a replica of the previous sum, so it should be pretty simple. By applying Kirchhoff's second law, if I apply Kirchhoff's second law, let's consider loop say AFCBA. In loop AFCBA, right? Now I'm moving from A to F, nothing there. I'm moving from F to C. The loop is being traced from F to C, whereas the EMF is sending current from C to F. The direction in which the loop is being traced and the current is being sent are opposite. Therefore, the EMF will be treated as negative. Now, I'm moving from F to C. The current is leaving the node at F. The current is leaving the node at F, right? Therefore, the current is going to be treated as negative. So, this is going to be minus I2 R2. Then I'm moving from C to B, nothing there. Then I'm moving from B to A. Current is entering the node at point B. current is entering the node at point B, therefore it will be treated as positive, right? So I1 R1, I'm moving from B to A. As I move from B to A, current, the loop is being traced from B to A, and EMF is sending current also in the direction from B to A only, right? Therefore it will be treated as, the EMF will be treated as positive, is 0. When I substitute the values here, I'll get a linear equation. Now let's consider in loop, let's consider the loop, say A B D E A, A B D E A, right? A B D E A. Now I'm tracing the loop from A to B. Now as I trace the loop from A to B, current is moving from B to A. The direction in which the loop is being traced and the current is moving are opposite. Therefore EMF will be treated as negative. I'm tracing the loop from A to B. Current is leaving the node at point A, or current is leaving node A, right? Is exiting node A, right? Since it is leaving the node, therefore it will be treated as negative. So minus I1 R1 AB. I've done. Now I'm tracing from B to D, there's nothing there. Then I'm moving from D to E. As I move from D to E, sorry, as I move from D to E, current is leaving the node, leaving the node at point D. Therefore, current will be treated as negative. I1 plus I2 into the external resistance R. So I moved from D to E, then I'm moving from E to A, there's nothing there. And then again A to B, so this is 0. So I'll get another linear equation here. Solve the two linear equations simultaneously, you should get your answer. Let's see another sum with Kirchhoff's law. Let's consider this circuit. This is 3 volts and 1 ohm. That means it will give an EMF of 3 volts and it has an internal resistance of 1 ohm. It is sending current I1 in this direction, right? Let's consider that this point is E, B, F, D, A and say C. Okay, let's consider this is 4 ohms, this is 5 ohms. Okay, now this is sending current in this direction. Let's assume current I2 is moving in this direction. Okay, this is say 4 volts and 2 ohms. Let's assume this is 6 ohms. This is say I1 plus I2. This is 10 ohms. This is 2 volts and 2 ohms. Right? Nice circuit. Now let's try to find out, or let's try to apply Kirchhoff's law in this circuit. Let's first consider.
So C2A, how much ohms?
How much?
C2A.
C2A is say 3 ohms. Right? Let's consider loop A, B, E, C, A. For loop of, first I will say by Kirchhoff's second law. For loop Let us consider the loop, say A, B, E, C, A. A, B, E, C, A. A, B, E, C, A. Current is entering the point at A, so therefore the current is going to be treated as positive. So this will be I1 plus I2 into 10. I'm tracing the loop from A to B. Guys, I'm tracing the loop from A to B. Therefore, current is that particular current will be treated as positive. So for internal resistance of 2 ohm, this will be current will be treated as positive I1 plus I2 into 2. That's your 2 ohm internal resistance. I'm tracing the loop from A to B, right? Now the EMF is going to be sending current also in the same direction. The EMF is going to be sending current in the same direction. So this is going to be plus 2 volts. Now that is my string AB. Now I'm going to move towards string BE, right? BE. This is current I1, right? Current is entering the node, therefore it will be positive. So this will be plus I1 into 4. I1 into 4, right? I'm tracing the loop from E to C. As I trace the loop from E to C, current is entering the node at E, therefore this will be 1 into I1, right? The loop is being traced 1 into I1, that is your internal resistance, okay? Now the loop is being traced from E to C. The loop is being traced from E to C, and the EMF is sending current also in the direction from E to C. Therefore this will be positive, right? Current is entering the node at point C. Current is entering the node at point C, therefore this will be positive plus I1 into 3, right? That's going to be my first loop, should be equal to 0.
Shouldn't that be positive?
Which one?
Minus 1 into I1.
Minus 1 into I1. Entering the node, I said positive, okay. My mistake, I must have written negative. Current is entering the node, therefore it is going to be positive, okay. Now let's consider loop A, B, F, D, A. A, B, F, D, A. AB. Current is entering the node at point A, therefore current will be positive. Current is entering the node at point A, so for internal resistance also the current will be positive. So this will be I1 plus I2 into 2, right? I am tracing the loop from A to B. EMF is sending current in the direction from A to B, right? If EMF is sending current in the direction from A to B, this current will be treated as positive, right? Then I am moving from B to F. As I move from B to F, current is entering the node at point B, therefore current will be positive. I am moving from F to A. As I move, F to D. I am moving from F to D.
So why did you have
2 is that EMF 2 volts. Okay. I'm moving from F to D. As I move from F to D, I'm tracing the loop from F to D. Current is moving from F to D. Therefore, the EMF will be treated as positive. For internal resistance, the current is entering the node at point F. Current is entering the node at point F. Therefore, current will be positive. So plus I2 into 2. Then I'm moving from D to A. Current is entering the node at point D. So that's going to be I2 into 6 should be equal to 0. Solve the two loops simultaneously. You should get your answer. Fine. So do we understand Kirchhoff's law completely? Right. We'll stop this here for the day. Thank you very much.